Welcome to Session 1 of the MOVI-C Control Cabinet Products Basic to Intermediate Training. You've completed the introduction, and this is our first session. We're going to sort of get you up to speed in basic concepts as well as some of the basic ideas about the product itself. I'm going to mention right now at the very beginning that we do chapterize these sessions on YouTube, so you can skip around. If there's something you already know a lot about and you don't want to listen to it, feel free to skip ahead. Also, please check the descriptions under each video because some of them include links to downloadable products that you may need as we go through the class. All right, let's dive in and talk about a few basic concepts. We're going to talk, first of all, just about how motors work and how variable frequency drives control them. Again, if this is really basic stuff you already know, feel free to skip ahead. But if this is new to you, I think this is going to make a lot of things make sense. So let's talk about AC induction motor construction. The AC induction motor is probably the most popular motor style in industry. It's extremely versatile. You can have tiny fractional horsepower AC induction motors. You can have gigantic monsters that generate hundreds of horsepower. It's a very versatile motor design, so it's the one that you will probably encounter most frequently. It is certainly one that variable frequency drives excel at controlling. So what are the parts of an AC induction motor? Well, of course, you have some things that are pretty obvious, like what's called the stator. The stator generates the magnetic field that causes the motor to rotate. Everything is enclosed in a housing, which is usually made of cast iron, steel, or aluminum. That simply encloses everything and protects it. Then you have the rotor, which spins inside the stator, and the motor shaft is attached to the rotor. Motors have end shields that are sort of like caps that close the ends and provide a place for the shaft to exit, usually through a seal that protects the interior of the motor. The conduit box contains the wiring. Conduit box goes by a number of names in industry. Another name is terminal box, and that's because it usually contains a terminal block or the wiring that you connect to the control system, or if it's just a line-operated motor, then to a switch system and probably some fuses or circuit breakers. So a motor really is not that complicated. That's one reason why motors can operate for decades if they're properly maintained, because they're very simple. They really don't have much to wear out. Now let's take a closer look at the rotor and the stator, because that's really what makes the motor turn. This is a typical AC induction motor rotor, and it looks just like a shaft with a solid cylinder of metal attached to it. Actually, it is a little more complicated than that. We use the term squirrel cage for this type of rotor. In fact, AC induction motors are sometimes called squirrel cage motors. And the reason is because inside what looks like that cylinder of metal is actually something that looks like this. It's usually made of copper or aluminum, and it's cast, it's inside there. And what it really is a giant coil. All those metal bars connected at the end are like a big electromagnet coil that has both ends shorted together. We call that the squirrel cage because it looks like the thing you find in a rodent cage of some kind, that your hamster would run around on. And the squirrel cage magnetically interacts with the magnetic field produced by the stator, and that's what causes it to turn, and of course it turns the shaft. So that's the rotor. Let's look at the stator. The stator is made from a magnetic material like iron or steel. It's actually a bunch of thin sheets of metal that are laminated together. We call that the core. The rotor fits inside it and spins in that hollow space within it. But the stator, in order to do its thing, has to be wound with a lot of coils of very fine copper wire. There are actually 3 separate coils that are wound around the core. The rotor interacts with the magnetic field that those coils generate. So what a motor really is, it's an electromagnetic machine. Now, the key to understanding how an AC induction motor works and ultimately a variable frequency drive requires you to understand that a magnetic field is developed inside the motor that rotates. Now, you may be thinking, well, how can a magnetic field rotate? It's just an invisible force field generated by an electric current flowing through wires. Well, let's take a look at that. Let's take a typical motor, and we pulled the rotor out, so we're just looking at the stator. Remember, the stator has 3 separate coils of wire, and these are connected up to a power supply that's really 3 power supplies in one. We call this a 3-phase power supply. Most industrial motors are 3-phase. They require 3 separate power supplies to energize the 3 coils of wire. Now, each power supply is generating an alternating current, where the voltage and the current rise and fall in an endless cycle of waves. We call this a sine wave. You may remember that from math class. If you learned trigonometry, you learned about the sine function. If you plot the sine function, it looks like this picture here. Well, a 3-phase power supply is 3 power supplies, each generating a single sine wave of rising and falling voltage and current, and those 3 power supplies are not working in unison. They are slightly shifted in time with respect to each other. That means that when they're operating, they're all at different places in their rising and falling cycles. The advantage of 3-phase power is it lets you deliver the maximum amount of energy to the motor. It's just a very efficient way of delivering electrical energy. So what happens is 1 coil in the motor is connected to each phase. So that means you're getting 3 magnetic fields that are varying in strength and polarity over time. Now, this is kind of what the motor looks like if you diagram it. You have these magnetic poles, and poles and magnets always come in pairs. You never have just one pole and a magnet. There's always a north and a south pole. So this is a set of poles. We call it A1 and A2. There's a second set. We call it B1 and B2. And a third set we call C1 and C2. Each one is connected to one phase of the power supply. They generate a magnetic field, and those 3 magnetic fields interact with each other, and they sort of average out so that they're pointing in a particular direction, which is what this arrow represents. It represents the direction the magnetic field is pointing. So at some point, the magnetic field is pointing between A1 and A2. However, as the power supply phases change in voltage and current, the magnetic field changes too. And what happens is that field appears to turn, sort of like this. The field rotates in time with the power cycles, and it goes around inside the stator. So that rotating magnetic field is really the key to how an AC induction motor works. It was actually a very important discovery, and it just revolutionized the use of motors in industry. Now, how does that rotating field make the rotor turn? Well, let's look at it in a little more depth. We've now put the rotor back inside the motor. You can see the ends of the squirrel cage there in the blue. So we have the rotor coil, we have the stator coil. The stator's generating that rotating field. The rotor's sitting right inside of it, right in the middle of it. And what is happening is, as that magnetic field moves, it causes an electrical current to flow through the bars of the squirrel cage. And that, in turn, generates a second magnetic field that surrounds the rotor. So we have 2 magnetic fields, the moving one in the stator, and a second one that is induced or produced inside the rotor. So, for example, if the stator field has a north and south orientation like this, what happens is the induced field has the opposite polarity. It's got a south-north orientation. And as you probably remember from grade school science, with magnets, opposite poles attract. And so what happens is the poles attract each other. The rotor and stator poles grab onto each other. And since the stator poles are rotating, they grab onto the rotor poles and make the rotor turn. And the rotor, because it's mechanical, can spin physically. And so we get mechanical motion, something like this. You can see the poles sort of track each other, and the rotor just gets dragged along, turning the shaft as it goes. It's a brilliant and simple concept. Now the question is, how fast is the motor speed? What controls the motor? Is it voltage? Is it current? And the answer is no. Actually, it has to do with how fast the power supply is causing the magnetic fields to change. You probably know in the United States, our power is what's called 60 hertz power. That means the sine wave is going through 60 complete cycles every second. If you're in another country, it may be 50 cycles a second, 50 hertz instead. That's just the way it is. The world is not unified on electricity. But I'm recording in the United States, so we'll say it's 60 hertz. So that field is changing 60 times a second. Now, if you multiply 60 seconds in a minute, that translates to 3,600 field changes every minute. So that magnetic field is spinning around inside the motor 3,600 times per minute. In other words, 3,600 rotations or revolutions per minute. And you're probably getting a clue as to how fast the motor will turn. So the motor, you can expect to be turning at about the same speed. We call this, and here's your first red term, the synchronous speed. Now the synchronous speed is the speed at which the magnetic field is rotating around inside the stator. That's not necessarily the speed the shaft will turn. It's the speed the field is moving. So in this case, the synchronous speed is 3,600 RPM because that's the speed that the magnetic field is going around inside the motor. Now, we come to something kind of interesting. There are different ways of setting up the internal poles of an AC induction motor. Now, this is the example we've looked at so far. We call this a two-pole stator. Now, you're probably looking at this and saying, that doesn't make sense. I count 6 poles. Where do you come up with 2? Well, the answer is you divide the total number of poles, 6 in this case, by the number of electrical phases. Now, this is a 3-phase motor, so if you take 6 divided by 3, you get 2. What that means is every phase gets 2 poles. So this is a 2-pole stator, but you can actually wind your coil to have more poles. Here's an example of a 4-pole stator. It's actually got 12 poles total, so if you take 12 divided by 3, you get 4. That means there's 4 poles per phase. If you look at this, you'll notice there's 2 A1s and 2 A2s, 2 B1s and 2 B2s, 2 C1s and 2 C2s. And that is because there are actually now 4 poles per phase. Why do we do this? Why would we want to create more poles? Well, the answer is that if you energize these motors with 60 hertz, which changes 3,600 times per minute, a 2-pole motor will rotate at 3,600 rotations a minute. But if you double the number of poles, it takes twice as long to work through them. So you go at only half the speed at 1,800 rotations a minute. So the more poles you have, the slower the motor goes. Motors are commonly sold in 2-pole, 4-pole, 6-pole, and 8-pole versions, and they all have different speeds. They get progressively slower as you add poles. And in the days before variable frequency drives, that is how you varied the speed of motors. You used different numbers of poles to achieve different speeds. Variable frequency drives were a real jump forward because they allowed you to have an infinite range of speeds between maximum and 0. Get to that in just a minute. Okay, now we come to something that confuses some people if they're not that familiar with motors. With an AC induction motor, we know that the magnetic field is spinning around at maybe 3,600 RPM or 1,800 RPM. It's kind of logical to assume that since the rotor is magnetically locked to the stator field, it should be turning at the same speed, shouldn't it? Shouldn't that shaft also turn at 3,600 RPM? Well, the truth is, it doesn't. It turns about 5% slower. Now you may wonder, well, why is that true? Well, it's because if the two fields were perfectly locked together and moving at the same speed, the motor could not develop any torque. There has to be that slight difference in speed to develop torque. There's a name for this, and here's another important red term. We call it slip. So all AC induction motors have slip. Their shaft turns about 5% slower than the magnetic field is turning. So even though the magnetic field of this motor is turning at 3,600 RPM, maybe the shaft is turning at 3,450 RPM, slightly slower. And that is why we get another name that we commonly use with AC induction motors. We call them asynchronous motors, which means simply that the rotor doesn't turn at the synchronous speed. It turns close to it, but not exactly. All right, that's probably familiar to most of you, but maybe for some of you that was new information. So there you go. So let's bring it all together. Motor speed depends really on two things: the frequency of the power you feed it and the number of poles in the stator. And there's a nice simple little equation that lets you calculate the synchronous speed. Simply take 120, multiply it by the frequency, and divide by the number of poles. And if you care to see how that equation was derived, there you go. If you don't, then just use it. But here's an example. If you have a 2-pole motor and you power it with 60 Hertz AC, the synchronous speed is 3,600 RPM. If you use 4 poles at the same frequency, it halves that speed to 1,800. If you go to 6 poles, it's 1,200 RPM, and 8 poles, it's 900. Now in Europe and many other countries, they use a lower frequency, 50 Hertz. Their motors turn a little slower at the same number of poles. You can see the European speeds there. They're a bit slower, but they're fairly close. And do remember, these are the synchronous speeds. The shaft is actually turning about 5% lower than that. But motor manufacturers always rate their motors by the synchronous speed, and they usually just tell you the approximate percentage of slip. So that's why we're using these kind of idealized numbers. So if you take one of these motors and just plug it into the line, you don't connect it to a variable frequency drive, you just plug it into, say, 480 volts, 3-phase, then it will turn at one of these speeds, depending on the frequency and the number of poles. It's really that simple. Okay, well, I hope that made sense. Let's move on and talk about something related. There is another kind of AC motor that you often see in industry as well, and it is called the AC synchronous motor. A good example of this is a servo motor. SEW-EURODRIVE sells a whole line of servo motors, actually several lines of servo motors, and they're a little different. They have a normal set of stator coils, but they also have a rotor that does not contain a squirrel cage. Instead, it has permanent magnets bonded onto the shaft. So if you ever pick up one of these, be very careful because it's a very powerful magnet and it will grab you. It's very aggressive because they're powerful permanent magnets. I usually pass one around to my class and I say, do not get this anywhere near your computer or anything metallic because it will go thunk very quickly. So synchronous motors have permanent magnets on their rotors, and because of this, you're not inducing a second magnetic field. The magnetic field is always there. What does this mean? It means one very important thing. It means they can turn at exactly the synchronous speed. So they turn at the same speed the magnetic field is rotating around inside the stator. That is one advantage of synchronous motors. They have no slip. And just by point of comparison, I've got the rotor from an AC induction motor, an asynchronous motor, and a servo motor, a synchronous motor. These motors generate similar torque, but you notice the servo motor is a lot smaller and it's definitely lighter. In fact, I usually pass these around in class and people can see right away there's a big difference in weight. Servo motors just have smaller rotors. They're also a lot more dynamic. In other words, they can start and stop and change direction more quickly. It's because they have a lower mass, so their inertia is lower. They can essentially turn on a dime, as the expression goes. They can also produce bigger peak torques, so they definitely have a number of advantages. Of course, they're also more expensive, which is why they're not quite as popular. But because of these qualities, they're often used in precision control tasks. You will find servo motors in CNC machines, robotic systems, anything that does precision positioning. They're very common. Okay, well, that is motors. I hope that made sense, and I hope you found that interesting. Now, let's clarify some terms before we go any further. I have been using the term variable frequency drive a lot since we've started, because that's what we're learning about. MOVI-drive technology is a variable frequency drive. However, there are other terms which mean exactly the same thing, and you should be aware of that. Variable frequency drive is frequently abbreviated VFD, and I will use that term. It's also called an inverter. These things all mean the same thing. So if you hear any of these terms, we're talking about the same thing. All right. So let's talk about the parts of a VFD. What goes on inside a VFD? Any VFD. A VFD is actually a pretty simple device. First of all, it brings in alternating current, usually three-phase. Some VFDs operate on single-phase, but we'll say three-phase, say 480 volts AC comes in. And the first thing it does is it converts it to direct current, DC. So it runs it through something called a rectifier. The rectifier converts it to a form of DC that pulsates up and down. Now that is a bit of a problem. You need smooth DC, so the next thing it does, it feeds it into a bank of filters. And these filters smooth it out. And it looks sort of like this. It looks like a fairly flat line with a little ripple at the top. That is direct current. And many VFDs have a set of connectors called the DC link. And that's a place you can externally connect to if you put a voltmeter on it. And if you do that, I advise you to do it with proper safety because the DC link voltage is usually around 700 volts DC. It's a very hefty voltage, and it will definitely do more than just bite you if you touch it. It could actually kill you. The DC link connection is used to power the VFD and ultimately the motor. In fact, some VFDs, if you have a high voltage DC supply, you can connect it to the DC link and feed the VFD directly with DC. For example, from a solar farm would be an example. And you could bypass the rectifier and the filters entirely. Okay, that is possible. We're not going to worry about that in this class. We'll just assume you're plugged into the wall somewhere. But anyway, you have that high voltage, fairly smooth, slightly ripply DC. That gets fed into some very hefty transistors. And they're called IGBTs, which stands for Insulated Gate Bipolar Transistor. An IGBT is like an electronic switch, and it can be turned on and off thousands of times a second with an electronic control signal. So there are 3 IGBTs inside the VFD. They're connected to that high voltage DC. The other side's connected to the motor. And the IGBTs are controlled by a little microcontroller inside the VFD that basically is pulsing those switches on and off somewhere between 4,000 and 16,000 times per second. And as it turns them on and off, this is what comes out. This is a kind of synthetic alternating current. Now, it doesn't look like alternating current. It looks like a bunch of pulses, but the motor sees this almost like it's a sine wave. The motor sees it as regular alternating current. But if you hooked it up to an instrument like an oscilloscope and looked at it, this is what it would look like. Now, we call this technique of creating synthetic AC pulse width modulation, or PWM. What we do is we adjust the width of the pulses. You notice they just go between on and off. They don't have any intermediate voltage values. It's just on or off completely. But the time they're on and off varies, and so that's the pulse width. So we're varying the pulse width. And it turns out that when we vary the width of the pulse, it allows us to create a form of AC of any voltage and frequency we want within the limits of our power supply. So what the motor sees is a mixture of mostly off, which looks like a low voltage, equally on and off, kind of a medium voltage, mostly on, a high voltage, and overall what the motor sees actually is a sine wave. So that's how the motor sees it, even though we see it as a bunch of just on and offs of different width. And that is really the whole thing behind VFDs. It's really that simple. Of course, the VFD does some very sophisticated things, varying the pulse width, and that is how it controls the motor speed and the motor torque and does all kinds of really nifty things. All right, so that is VFDs in a nutshell, 5-minute discussion. Hope that made sense. Hope you found it interesting. Okay, well, we've gotten some of the basics out of the way, so now we're going to go ahead and move on and talk a little bit more specifically about this class. We're going to talk about what we're covering and what we're not. But first of all, I'd like to answer a question that maybe you've been curious about since this is in the title of the class. What do we mean when we say control cabinet products, MOVI-C control cabinet? Does that differentiate them from other MOVI-C products? The answer is yes, it does. Let's talk about it. Control cabinet products, which are the ones we're going to study, as the name implies, often spend their lives living in a central location, usually some kind of control cabinet. Now, some of them just get bolted to a wall or a machine out in the open because maybe the environment isn't very demanding and it's safe just to leave it out there. But in general, they stay in a control cabinet. And the reason they do this, of course, is for protection, because many industrial environments have all sorts of threats to electronics, like solids that could get inside, dusts and other things, and especially liquids like water or other materials that could get in and wreak havoc with the electronics. In fact, many electronic devices come with a rating called the IP rating. IP is simply a pair of numbers that indicates a device's protection against solid and liquid entry. So for example, an IP rating might be something like IP20. The 2 and the 0 indicate how resistant that object is to solids, that's the first number, and the second is liquids. Now you can guess IP20 means it has some resistance to solids, basically large objects getting inside, but 0 doesn't sound very promising. And you're right, something with IP20, you better keep water far, far away from it because it can get right in there. You may have encountered the term IP when you bought your most recent smartphone because most phones today have fairly high IP ratings, meaning you can drop them in water and they will survive just fine. So some electronics products have very low IP ratings, meaning they really need a lot of protection, and others are very well protected and can just be right out in the most hostile of environments. Well, most control cabinet products have an IP rating of around 20, which means they will keep out large objects, and that's about it. Definitely nothing wet. So they depend, as you can guess, on the cabinet to give them protection. So that's one of the reasons they're inside the cabinet. All the cables converge on the cabinet, and that ranges anywhere from little skinny communication data type cables to big fat heavy cables carrying relatively large voltages and currents that power the motors. So that's kind of the idea of control cabinet products. So we're going to be focusing on the MOVI-C products that are meant to live inside a cabinet. In contrast to that, there is a second category of product called decentralized products. These products are quite different from control cabinet as far as the way they're deployed in the industrial environment. It's near the application. Instead of sitting in a box maybe far away from the application with wires running long distances, it's usually parked right next to whatever it is it's driving. In this case, you can see we have a baggage conveyor, and there is a MOVI-C decentralized product nearby turning that conveyor. These rely on their IP rating to provide protection, and most of these have pretty high IP ratings, so they can sometimes just be washed down by harsh chemicals, such as those used in a poultry processing plant, or maybe something a little less aggressive, or maybe they can just be in an environment where they might get rained on or where it's just very dirty. The point is they don't need a cabinet. They have coatings and seals and other things that protect them from their environment. So they have a higher IP rating. And most of the cables that go to a decentralized product are local cables. They pick up power somewhere nearby, and if there's a cable that goes any distance, it's probably a little skinny data cable going off to a controller or a PLC or something like that. So it's really just a different philosophy of operation. And by having both control cabinet and decentralized products in the MOVI-C portfolio, we cover just about any conceivable application you can think of. So the MOVI-C generation is very thorough. It includes products of all sorts. But we're not going to be learning about all of those today. That would be a huge course. We're going to focus on the products that live inside the control cabinets. Now, a few MOVI-C big ideas. The control cabinet product line, which is what we're studying, is a unified family. It has 4 distinct branches of product, and they have a lot of similarities, but they have some distinct applications. They're designed to cover specific application needs. Each branch has unique capabilities distinct from the others. That's why we have 4 different branches. Again, we're just trying to cover every possible base that a customer might need to drive just about any kind of application. Okay, and finally, one quick clarification that will make things make a lot more sense as we work our way through the course, and that is the way MOVI-C products are named. Most product names in the MOVI-C line have 2 parts. The first part begins with the word MOVI, for example, MOVI-Drive, and then there will be an all lowercase name that comes right after it, like technology. So the complete product name is MOVI-Drive Technology. What we will be doing in these presentations, we'll usually be making the lowercase part in blue just to kind of make it jump out at you. But that is the way most names work in the MOVI-C product line. You've got those 2-part names. So don't let that throw you, but you'll see a lot of those. So let's take a look at sort of the forest. I've been talking about the trees. Let's get a little more specific and find the forest and all the trees. What are these 4 branches? Well, the first one is called MOVI-Track Advanced. It is a single-axis VFD. That means it's designed to operate basically a single motor. And it's usually, not universally, but usually controlled over a field bus. So this is one of our more recent products. It's just coming over into the United States right now in early 2023. By the time you watch this video, chances are it's going to be readily available, but it's a relative newcomer to the MOVI-C line. The next product in the MOVI-C line, the next branch, is called MOVI-Drive Technology. That is the focus of this class. It too is a single-axis VFD, and it too is often controlled over a field bus, although it doesn't have to be, and we'll be learning ways that you don't need a field bus. You may say, well, what's the difference between that and MOVI-Track Advanced? They seem pretty much the same thing. Well, MOVI-Drive Technology can do everything MOVI-Track Advanced can do and a lot more. It's got a lot more capabilities, it's more powerful, it's more versatile. So it's MOVI-Track Advanced plus a bunch of other things. So it's moving up the scale and power. Then there's something called MOVI-Drive System, which is also a single-axis VFD. In fact, it comes in exactly the same sizes as MOVI-Drive Technology. I'm showing you a picture of a bigger one, but there are many similarities to the hardware. But it can do more because it usually requires an external controller. That's a digital controller, almost like a small PLC. And what it does is it controls that VFD and it extends its power enormously. So MOVI-Drive System, again, is a step up in power for those even more demanding applications. And then finally, the 4th branch is MOVI-Drive Modular. This is the first one I encountered back in 2016. It's one of the first ones to come out. It is a very powerful multi-axis VFD, meaning that it can control a whole bunch of motors. That's really its forte, is controlling lots of motors. And it too almost always requires a controller to operate it. The controller is that orange box with the SEW on it sitting next to everything else. It's all wired together very neatly, as you can see. And it controls all those individual VFDs that are controlling different motors. So that is the MOVI-C control cabinet family, the 4 product branches that make it up. We will not be looking at MOVI-Track Advanced in this class. It's brand new. I've just gotten a hold of one very recently. We will eventually, of course, be developing a training for it. So keep an eye on the YouTube channel. Something like that will be coming out somewhere in the future. And I'm eager to prepare that training, but that's not the job for today. We'll be talking about the other 3 branches, primarily emphasizing MOVI-Drive Technology, which is what our class really centers upon. Now, what is not in this training? What are we excluding from it? Well, we are not going to cover the decentralized products. There are a lot of decentralized products. Again, look for a training for these in the near future. We definitely will be preparing trainings on these. These products right now include MOVI-Gear Performance, MOVI-Mod Advanced, MOVI-Mod Flexible, and MOVI-Mod Performance. These are exciting products. I've started working with them and I just love them. And I can't wait to prepare a training for these either, but we're not covering them in this class. But be aware of this. I've sort of hinted at this before, that when you learn about the tools for the control cabinet products, a lot of what you've learned apply to the decentralized products. A lot of that knowledge transfers across almost effortlessly. So you could sit down with a decentralized product after taking this class and probably figure out at least how to do basic things with it without any further training. I know I did. And I was very impressed. Again, it's that consistency idea that we have with MOVI-C. But we will not be covering those products here. We're also not going to talk about the B generation products. Things like MOVI-Track LTE-B+, MOVI-Track LTP-B, the MOVI-Track B, and the MOVI-Drive B. MOVI-Drive B, as I've said before, there's a class already on YouTube. If you want to learn about that, plunge in. It's a fantastic course. I'm actually at this time preparing classes on the MOVI-Track LTE-B and LTP-B. Those will be coming out sometime in the months ahead. There will certainly be trainings for these, but we're not covering these either. It's just not possible to cover all our electronics in one course. It would be gargantuan. We have a huge electronics portfolio. Let me give you a helpful hint just to help you get oriented in all these products and all these product branches. MOVI-Drive technology and MOVI-Drive system are relatively simple products to learn, and I will say they are roughly, and I stress roughly, comparable to previous generation VFDs like the MOVI-Drive B, which was our flagship product for many years. You can use these to do the same kind of applications that MOVI-Drive B could do. They're powerful, they're flexible, they can do a lot of those really hefty things. So if you are an existing customer and you want to move into MOVI-C and you've been using MOVI-Drive B, take a look at MOVI-Drive technology and MOVI-Drive system because they have great similarities in their capability. Although I would say they also go beyond it in many ways. They're really excellent products. However, MOVI-Drive system, because it uses a controller in most applications, can do even more. So if you have a more complex application, MOVI-Drive system is probably the better choice because it goes beyond what MOVI-Drive technology can do. For this class, we are focusing on MOVI-Drive technology. Almost everything you learn, though, is going to apply to MOVI-Drive system and MOVI-Drive modular. So we can't cover all three of those. Again, it would make the class too complicated. It would also mean you'd need a demo unit with multiple MOVI-Drives. So we are focusing just on the technology product. We think that gives you the most bang for the buck for this class. But the wonderful thing is a good percentage of what you learn directly transfers to those other products. The main difference is that you connect to a MOVI-Drive system and a MOVI-Drive modular using a different strategy than you do with MOVI-Drive technology. And also MOVI-Kits, those application modules, work a little differently. I will touch on those briefly and demonstrate a few things with MOVI-Drive system and modular because I have demo units for them and I will show them to you, but we won't be doing any lab activities with them. Obviously, we're not asking you to get a hold of all three products. So be aware of that. MOVI-Drive technology is really this class's focus. Let's talk about our new engineering software. If you are familiar with our older products, then you have probably encountered MOVI-Tools Motion Studio. That is the software that many of the B generation products used. And it's been a workhorse for many generations. But we decided new generation hardware, we really need new generation software. We could not extend this product further. Plus, in many ways, this product really does feel like yesterday's technology, and we didn't want to marry that to a brand new product. So if you've been using this, that's great. Again, we have classes on how to use it. It works wonderfully well for our older products. Of course, we have a few other pieces of software for those too, like LT Shell you may have used. However, these have nothing to do with MOVI-C. So we are going to transition from this to our new software, which I think is just incredible. It is called MOVISUITE. And this is MOVISUITE Standard. It comes in several levels. This is the free one. You can do an enormous number of things with it. You can just download it from the website and go. This is the C generation software. The beauty of MOVISUITE is that it works with all the MOVI-C products pretty much. So once you've learned it in a class like this, you'll be able to transfer that knowledge directly to other control cabinet products that we won't be studying in this class, also the decentralized products. It's just a unified package. And so I think you're really going to like MOVISUITE. Plus, it's designed to today's software paradigms, so it's very graphical. It's very easy to work with. I think you're going to like it very much. I know I certainly do. When I first saw it in 2016, I said, this is really going to be a pleasure to work with. Let's compare it to the previous generation software, MOVITools Motion Studio. You can see it's designed to do essentially the same tasks. Of course, motor commissioning and startups, doing programming when that's necessary, doing diagnostics, and it has one additional feature that used to be a separate software product with the B generation, and that is functional safety programming. We will not be getting into that here. One question a lot of our customers ask us, you've just brought out a new generation of products. Does that mean the old is going away? Is that like my cell phone, that as soon as the new one comes out, the old one basically has to go in the bin? The answer is no. SEW-EURODRIVE is very good at supporting its older products for a reasonable length of time before they start phasing them out. Let me give you kind of a timeline just to give you a feel for where things go. MOVI-Access, MOVI-Drive B, MOVI-Track B, those are kind of the major products of the B generation. And they've been around a long time, and you can still buy those products or encounter them frequently. The C generation started up around 2016. MOVI-Drive Modular came out first, then MOVI-Drive System, MOVI-Drive Technology, and MOVI-Track Advanced is emerging right now in early 2023. And you can see the idea here is that the product lines are going to run in parallel for a while. You'll be able to buy the older ones in many cases. We'll certainly support them. We'll certainly be doing trainings in some of them. Now, eventually, of course, there will be a point where we terminate those products. We stop selling them. Of course, service will continue a little beyond that, but they will come to an end of sale at some point, but we don't have dates on that yet. So we can't really tell you anything else at this point, but do be aware SEW is not the kind of company that just drops a product the minute it ceases to be the latest and greatest. We are very good at taking care of things. So on that cheerful note, I'm going to end this session. So this is the end of session number 1. In session number 2, we're going to start digging into the details of the MOVI-C control cabinet products that this course is covering. So looking forward to seeing you then.